example I want to examine with you is slightly more complicated, but it's going to use the exact same magnetodynamic template that we used for the electromagnet. And we're going to use that template to solve a problem that's a bit more complicated because it involves an external circuit. But this will allow us to model our real practical, let's say, a non-trivial electromagnetic dynamic application, which is a single-phase transformer. So you see it here. It's again a 2D model, quite simple geometrically. So in practice, if you do an actual design, it's going to be a bit more complicated, but this is already actually quite nice because it has all the main ingredients that you need to do transformer modeling. So we exploit symmetry again, right? You have a symmetry plane or curve over here. So you can imagine that you have the same geometry mirrored for the, let's say, negative values of y. And here you see in the middle you have a magnetic core. And then you have a primary winding on the left and then a secondary winding on the right. And the idea would be, if I impose here a current that varies in time, I will get over here, since the flux that is channeled through the magnetic circuit is time varying, then I'll see in here a variation of the flux in time, which will lead to electromotive forces taking place in the secondary winding. And if I close my windings on a load, I will have a current. And so in order to do that, we could, if we wanted to do a very simple test with no load, for example, we could do it without circuits. We could impose the voltage or the current over here. And then we could basically measure voltage over here without current. But if we want to be realistic, what I would really want to do is to derive what is called the exterior characteristic of the transformer. So basically, I'd like to be able to connect the secondary winding to a load. And I would like to do a simulation where the current that is flowing in the secondary, well, we also flow in a load. So I need a way to represent these discrete or lumped circuit elements. And so for this, I will need to do circuit coupling. So let me show you how we do this with the template library without changing the template at all. So let's first open the template library to examine what we have skipped for now. Well, I alluded to this already in the previous lecture. So flag circuit coupling, we'll need to set this to 1. And if we search for this flag, so flag circuit coupling, you'll see that if the flag is set, then you have additional groups that are defined. They are empty by default, in the same way that these groups here for, let's say, my actual materials that I meshed are empty. Well, what do I need? Well, I have a group, an abstract region that will contain voltage sources, so source V. Sir is to say, okay, this is a circuit, so this will not be linked to a mesh. Okay, this will be like a virtual region, so it's not represented in the mesh. It's going to be like if you did a circuit modeling in SPICE or in Simulink. Well, this will contain, let's say, nodes in a circuit representation of a circuit with lumped elements. So this for voltage sources, this for current sources, this for resistances, this for inductances, and this for capacitances. This here you can ignore. It was an example to show you how you would treat nonlinear, let's say, impedances in this case to model diodes, for example. Okay, what else? Well, you need to define, let's say, these regions where you're going to put your lumped elements, but you also need to define the function, so the impedances, or in the time domain, your inductances, your resistances, your capacitances. And it's done here. Basically, you have one function that will be defined, again, piecewise. You have the same flexibility as we have for the regions for actual materials. Well, we have the same flexibility for lumped circuit elements. So I have a single function to define resistances, but the value will depend on the group on which it applies. And then we can do the same thing for inductances and capacitances. And that's it, actually. So these are the things that we'll need to define. So let me go down a little bit to show you that there is no magic, because of course you need some equations for this. And so the way the equations are written, Well, it's exactly the same as the global quantities that we derived in the weak formulation, except that we need to couple them with additional circuit equation terms. And so these circuit equation terms, well, you can have a look. They are written in a very simple way in a resistance circuit. So in the resistive elements, what do we have? Well, a relation between U and the current through the resistance. Okay, and okay, we have a way to write this equation in terms of the current, because basically this allows to identify basically what are the primary variables in the circuit formulation that we write. So this, I'm not going to go into the details. Let's just assume that I wrote this correctly for you. And so you see here, the most important thing is that indeed in the resistance part of the circuit, well, you have U equal to R times the current. What about an inductance? Well, same thing. You have U as the time derivative of the value of the inductance times the current. And then in the capacitance, you have the relation I is equal to the time derivative of C times the voltage. Okay? And then you have a global equation that will link basically, so you have an equation of network type that will link these quantities. So basically, we say that I are the node unknowns, U the loop unknowns, and the equation in terms of I. And we do this for all the, let's say, quantities, the actual currents that we have in the conductors, the currents in the stranded inductors, and the currents in the circuit. And they all obey the same, let's say, Kirchhoff's laws. All right? So what is really of interest for us is to use this in applications. And so let's have a look at the transfo.pro example. So this is the one for which we already looked at the picture. Oops. I have a few parameters that I made available. Again, the permeability of the core, a frequency, and then the type of conductor. I want to show you the effect of either coils or the academic case that does not really exist in practice, except in very particular cases where you would consider a massive conductor here, so a big, let's say, piece of copper to do the winding. So with a single turn, in practice, it's going to be coils. So if I run this, what do we have? Well, we have currents that I imposed in the primary. So the current is rotating like this, and this generates a flux density that is channeled through the magnetic core. And if we look at the magnetic vector potential, just the Z component, we have indeed the flux lines that are as we expected. Okay. You'll see that it's very similar to what we did for the electromagnet. Well, with some additional things. So first, well, we can check what we include there, transfo common. And so you see here that there are some dimensions that I make available and some physical regions, so nothing really spectacular. Some functions over here, some constants, sorry, that I make available in the interface. So the conductor type, massive or coil, the frequency, and then the relative permeability. And then we have some physical regions, so same thing, air. Here you have the external surface, so we didn't even play with this annulus to apply the infinite transformation. You could, in your example. Here I made something simpler, have the core. And then this is important. We're in 2D, and we want to model. So let's maybe look at the two files at the same time. Or maybe not this one. Let's open this one, yeah. So we want to look at everything in 2D. And so this is my primary. In order to have my currents flowing in the right directions, I will need to make sure that I identify correctly different parts of the coil, right? Because the current if it goes out here, it should go in there. So I should make sure that, let's say, all the directions of my currents are correct. And so the way I do it, I separate my coils into positive P, so plus, and minus or negative sides. So coil 1P, coil 1 plus, coil 1 M, coil 1 minus. So let's have a look. So this is coil 1 minus over here, and this is coil 1 plus. This is coil 2 minus, this is coil 2 plus, okay? So I have 4, let's say, parts in my coils, and I group them in coil 1, coil 2. So coil 1 is the primary, coil 2 is the secondary, each one made of 2 parts, positive and negative, plus and minus. And then I fill my regions, like I did before. So that's easy. What's the magnetic domain? Air, coil, and coils. If I have conductor type equal to 1, meaning I have a massive conductor, then I put everything, all my coils in vol C. If they are stranded, I put them in vol S. And that's it for my groups, actually. Well, that's it, except that if I do circuit coupling, I'll need to basically create my lumped circuit elements. We'll do that later. What about my functions? Well, what I do in my functions is the same as I did before. I need reactivity, that's it, conductivity, that's it. And then here you see this is the interest of actually keeping the parts of the coil separate in this 2D model. I will define a sign for the branch to fix the convention of my positive currents. So +1 along the z-axis, pointing up, and -1 if it's pointing down. So the coil 1P, I assign the value of the function piecewise to 1, and coil 2P to 1, and then in coil M, I assign to -1. Remember, if I have a stranded inductor, I also need, so in the case conductor type is equal to 2, I need to specify the number of turns. Okay, here I have a transformer where on the primary I have 100 turns, on the secondary I have 200. And then I need the surface of my coils, that's easy, right? It's just surface area. And then I need my JS0, and here you see I will use piecewise my sine branch function in such a way that my, let's say, unit current, it has the right sign in the positive parts with a plus, in the negative parts with a minus. The geometrical coefficients actually also need the sign, and they also need the thickness that was defined in the comment file. Okay, so up to here, I think nothing new compared to the electromagnet. The new things arrive here. I want to do circuit coupling, so I would like to exploit my global quantities, U and I, but I would like not to fix necessarily U and I would like to be able to impose a relation between U and I through additional equations, which are circuit equations. So how do we do this? Well, first, we need to activate circuit coupling. So I say flag circuit coupling equal to 1. Remember, when I will include the library over here, since I defined flag circuit coupling to 1, well then I will not use the default value anymore from the template. I will use the value that I specified here. So how do I write my circuit coupling? Well, I will basically first create my lumped elements. How do I do that? I basically fill my abstract regions. Remember, I had my resistance region, inductance, capacitance, and then voltage and current sources. Well, let's do it. So how do I do that? Well, I create now regions which are not linked to the mesh. And so here you need to invent numbers. So it's like inventing node numbers when you do a netlist in a circuit simulator. So here I will invent a region with number 10,001. And I will call it, and I chose names that are going to be easy for me to remember, E in. It's going to be a voltage source. Why? Because I add it in source V source. So when I do plus equal, it means that I take the region list as I had it before, so source V here was empty, and I add to it E in. So this is E in is going to be my voltage source. Of course, I'll need to define what I do in E in, right? But here I define my lumped element, which is a voltage source. I also add Rin, which will be a resistance that I put in series with my voltage source to be a bit more realistic. And then on the secondary side, I will define Rout, which is a load resistance. And I also added in my resistance, my list, let's say, of lumped resistances. Okay, so if I try to draw this, so let's maybe go back here. And so what I really want is to have here a voltage source, In. I would like a little resistance, Rin, in series with it. Then I would like actually to feed my coils. So here I will have my finite element model with the primary, right? And then I have my coupling. I'll have my secondary. And then I would like this basically with R out. Okay, so this is what I would like. And all of this here is my finite element model. So how do we do that? We'll see it's quite easy. So the first thing that we can do is to define actually the values of the functions on these groups, right? We define, for example, resistance SIR, the list of all the resistances in my lumped circuit model. Well, I will define my function now, resistance. Remember, this is the function that I need to define to give the values. Well, I define here that Rout, the function resistance on Rout is 1 to the 6. So since we work in MKS units, so it means that I put 1 mega ohm here on the secondary. So it's going to be almost an open circuit, right? And then of course you can change this. And Rin, I choose a very small resistance in series with my source, so 1 milliohm. Okay. And here you see I define some little constants. Val in, you'll see where I use this 1. So I will apply 1 volt, and this is a phase. Okay. How do I use, let's say, these values? Well, look. Constraints. On the magnetic vector potential, I don't do anything fancy. On the external boundary, I say 0, meaning that I have no flux going out. My current in my conducting domains and my voltages in my conducting domains, I don't need to supply anything, because instead of forcing the current and the voltage, I'm going to play with the circuit quantities. So I don't force any current, but I force a voltage. So in In, what am I going to do? I will force the value val In. And then I give a time function, because this way I will be able to do actually, without doing the, let's say, discrimination between frequency and time domain like I did for the electromagnet. Here I use actually a built-in function, which is cosine of omega t plus p, where I provide omega, 2 pi time frequency, and p, so the phase, explicitly. And this way we can actually use a single constraint both in the time domain and in the frequency domain. So I'll show you both in a minute. This is not enough, of course. Now I need to do the link, the circuit link, and now this is the first time you see it. I have a constraint of network type. The way to write this is quite easy. In our case here, we'll have 2 circuits. We'll have 1 circuit for the primary and 1 circuit for the secondary. How does that work? Well, we basically need to link all these lumped regions that we defined together with the finite element calculation. And you see it's done in a very natural way. The way we do it is as follows. Basically, we want to connect the plus and minus coil portions in series. Okay, and I want in series to also add my source In and my input resistance Rin. And the way I do that is I define branches. Branches go from one node to another, And here again, I need to invent some numbers. Let's go to, let's say I could maybe try to have, how do I do this? Let me maybe close this one. Yes, and let's, yep, do this, yep, and do this. Here we go. So I have my circuit, and let's try to understand what I'm doing over here. So I want to have my source E in, and I say these are two numbers that I invent. I basically put some labels on my circuit, and I say that this is E in is between nodes 1 and 4. Okay, you could put any number here, it doesn't matter. So, and these numbers are only, let's say, meaningful within one circuit definition. So it doesn't matter which numbers you take. The important thing is that you see behind this there is an algorithm that will basically construct your topology of the circuit. And so these are basically like tags or little flags that you basically, some names that you put to the nodes of your circuit. And so I say that E in is between 1 and 4, and R in, I say it's between 4 and 2. So 4, and this I call 2. And so what else do I need to do? Well, I have the plus and minus parts of my primary windings. Well, what should I do? Well, from 2 to 3, I'll say I have the plus. 2 to, let's say, 3, I'll have the plus winding. From 3 to 1, I have the minus winding. Okay? And so I should have maybe drawn them a little bit differently, right? Let me do it, because plus and minus, actually, it would be nicer. I'm going to remove this. Tuk, tuk, tuk. Let's do it nicely. How should I draw this? No, maybe not like this. Maybe like this. I put here 3. Oops. And so here I have my plus winding, and here I have my negative winding. Okay, so coil P is between 2 and 3, and coil M is between 3 and 1. Okay, and then for the secondary I can do exactly the same thing. R out, I define it to be between 1 and 2. Here 1 and 2 has nothing to do with the 1 and 2s in the circuit 1. This is just independent numbers. So R out, if I say it's between 1 and 2, well, I'll have my two finite element regions over there with a middle node that I call 3. Okay, and so this means that I have in series with E in, I have R in, and then in series with E in and R in, I have coil 1P, in series coil 1M, and I close on E in. Okay, and so that's my circuit definition. And actually, that's it. Because once you have that, you have linked all your quantities, and you are able to actually do a calculation with circuit coupling. In order to exploit this, it's nice to look at global quantities. And so over here in the frequency domain, what I do is to actually export U and I on E in, and U and I in the load resistance, so we can check what's happening. So let's just run the calculation once. Actually, we already did it in a file, so if I output this file, this is what I got. So the voltage on region 10,001, so on the voltage source, I have 0 real part, well, almost 0, right? 10 to the minus 17, and 1 imaginary part. This is because I apply phase shift over here, phase shift, which is phase E in, which was 90. Okay, so I apply a purely in the frequency domain imaginary voltage. And this is the current that is flowing through, let's say, the source. And if I look at the secondary, I have a voltage, a real part of 20 millivolts, and an imaginary part, so in phase with the source, of almost minus 2 volts, right? Minus 1.98 volts. So I apply 1 volt, I get 2 volts outside with an open circuit. Remember, I considered here R out, which is huge, 1 mega ohm. So almost no current. So if I apply here 1 volt, over here I should get, if I have my current I2, which is almost 0, I should have the ratio of the number of turns. What is the ratio of the number of turns that I provided? Well, hopefully it's 2, right? Let's have a look. What is NS? Yes. So NS coil 1 is 100, NS coil 2 is 200. So I have 100 turns the primary, 200 turns the secondary. And so the voltage I should get over here should be almost 2 volts, which is what I get. Okay? And the current, of course, is very, very small because I have a huge load resistance. If I want to change the simulations I make, so I could do the exterior characteristic. What is the exterior characteristic? The exterior characteristic is sorry, the voltage I will get on the secondary in terms of the current I get in the secondary for varying loads R out. So here I have a huge R out, which I fixed over here. Well, I could do the calculation now with a small resistance, right? I could do 10 ohms maybe, and I could redo the calculation. Transfo. Now, actually, clearly now you also see that I have some currents, right, in the secondary. So I have a small load and I have some current. I still have 1 volt on the primary. Now I see that on the secondary, I have a smaller voltage, 1.73. So before I was over here, right, extremely small current. Now I'm somewhere maybe over here. So the voltage decreased and now I have a significant current flowing in the secondary. So with this, it means that you have everything in hand to actually do a full study of a transformer. Because you can modify what? You can modify everything. You can modify the number of turns. You can modify the magnetic characteristics. Over here, the core was assumed to be non-conducting, but you could actually make it conducting. You could add it here, right? You could add it in the volt C. You can vary the loads. You can vary the sources. And so in the linear regime, actually, you have everything in hand to actually do the modeling of a transformer. You can change geometry. You can change everything. You can even do much more complicated transformers. You could imagine having, for example, a transformer. Well, first you could change the geometry, right? Because the geometry that I have here is not very realistic. If you look at an actual transformer, it's going to look, well, more like a shell-type transformer where you will actually have the primary winding and the secondary winding wound on top of another, instead of having the cartoon kind of transformer of core type that we have in the little example. You could have multiple windings. Nothing prevents you of adding additional circuits over here. You can do whatever you want, pretty much. And so what you will do in your homework is actually to model a 3-phase transformer. So we'll talk about it later, actually, and we'll probably have some, let's say, discussions about how to model a 3-phase transformer, but I will leave you to it to actually explore with whatever source you want how a 3-phase transformer works. So you'll have basically 3 pairs of windings, so primaries and secondaries for 3 phases, and I will ask you to do a design of these 3-phase transformers based on this template, right? Because you saw we haven't changed the template at all. I would probably advise to do the modeling first in the frequency domain, and then you will be able to extend it if you want to the time domain, and you could actually extend this to nonlinear behavior of the core to take into account saturation of the core. And this can be done basically by extending the model that we just analyzed together. To finish, let me just show you, we could run this model in the time domain. So let's have a look. So here in the frequency domain, what should we do to run in the time domain? Well, we should just define flag frequency domain equal to 0, and all the rest could work as is. So we can try it. So we can define flag frequency domain to 0, and we should define, right, initial time, final time, time step, etc. But I have some default values, so let's have a look if this actually works without doing anything. Okay, so in the frequency in the time domain, well, you have basically the time evolution of the quantities, right? Here for, let's say, cosine excitation as well. And you see that basically now you can simulate your transformer in time. Okay. With that, I'll finish, and I'll let you play with the transformer model and start to extend it for the three-phase case.